In exercise 947, we're going to be changing the position of a pi bond. Now, when you see a pi bond, instantly you should be thinking, what I can do with that is addition. And that suspicion will be confirmed if you compare that with the product. If the pi bond goes away, the way you can get rid of a pi bond is by doing an addition reaction. The other thing you'll notice here is that you don't have a pi bond in one place and you create it. And the way that you create pi bonds is through elimination. So at the very least, whatever else we have to do here, we know that we have to do at least one addition and at least one elimination. The one that we do first is the addition, because we have the pi bond to start with, and that's what you need to do an addition. To do an elimination, you have to have a leaving group, and we don't have that in our starting material. So we're going to do an addition. Now we've seen in the previous examples, when you do this addition, you want to add something that puts a leaving group on the molecule, because whatever you add is ultimately going to come off. If you compare the starting material to the product, you don't have any bromines or chlorines or iodines. You don't have any OHs on there. All those things that you learn to add onto a molecule in this chapter, none of that is on here. So whatever we put on here in an addition reaction, we're going to have to take off. And so whatever we put on should be a good leaving group. Now the best leaving groups are the halogens. They're very simple and they're very easy to work with. They're toxic compounds, unfortunately, most of them, but they are good leaving groups. So we want to add a halogen, and as we saw in the previous exercise, the way to add a halogen that if you're trying to remove the halogens in this chapter, the easiest way to add a halogen is to do hydrohalogenation, and it could be HBr, it could be HCl. And the reason why that's so good is because it only adds one leaving group, so you only have to worry about taking one thing off. The other ways of adding halogens that we learned in this chapter was just halogenation. So if you just used molecular bromine, for example, but that would add 2 bromines on, and so you'd have to worry about taking 2 leaving groups off of the molecule, which is kind of a hassle. And then halohydrin formation if you used molecular bromine in water. That would add a bromine and an OH onto the carbon chain. But that, again, would have 2 leaving groups, and it's kind of a difficult thing. That makes it more difficult to have to remove 2 leaving groups rather than just 1. So here, we're going to add H and Br, and that's going to put just 1 leaving group on the molecule. Now we want to walk the electrons. We want to walk the reactive part of the molecule slowly toward the other side where the double bond ends up being. And so here, we want the bromine to go as far right as possible. We want it to go here. In other words, we want the bromine to go on the carbon in the double bond that is 1, 2, 3 tertiary. That means the hydrogen would go on the other carbon. That's only bonded to 1 carbon. That carbon is primary. So we want the hydrogen to go on the less substituted carbon. That's Markovnikov addition. So we would not add peroxides here because we want hydrogen to go to the less substituted carbon. We want Markovnikov addition. So if you just add HBr without peroxides, the hydrogen will go to the less substituted carbon, the bromine will go to the more substituted carbon. I'm going to erase the hydrogen because it's implied in this structure, skeletal structure. Okay, well, now that we've done that, we clearly need to eliminate this from the molecule. If you compare this structure with the final product you want, you notice the bromine is not there. So we definitely want to eliminate it. Further, we want to eliminate it so that the electrons move toward the right of the molecule. We want to move the reactive part of the molecule, and the reactive thing is either the pi bond or the leaving group. We want to move that further to the right, further to the end where we want it to wind up. So we want to form a pi bond here. Now think about the different ways you can do an elimination reaction here, the different products you could get. You could either steal a beta hydrogen going to the right, in which case you'd form a pi bond going to the right, or you could steal a beta hydrogen going to the left, in the left direction, in which case you would form a pi bond going that direction. You might also think that you could steal a beta hydrogen going up, but notice that there's symmetry in this molecule both of these carbons here are methyl groups attached to what was the alpha carbon. They're both in the same environment. And so if you take this molecule and you sort of flip it upside down, you end up with the pi bond going up. So the pi bond going up or going to the side is really the same in this molecule. And the one that we want is this one where it moves to the right, where it goes closer to where we ultimately want it to end up. Okay, well, this alkene on the right is tri-substituted. The alkene on the left is di-substituted. So the right alkene is the more stable Zaitsev product, and the di-substituted one is the less stable Hofmann product. So we want the Zaitsev product, and the way that you get the Zaitsev product is by using a skinny base. That would be something like sodium hydroxide, sodium methoxide, or sodium ethoxide, either one of those. I'm going to use sodium ethoxide here. You could use any one. So we don't want the Hofmann product. Well, the way you would get the Hofmann product is by using a bulky base. We're not going to do that. We're going to use a skinny base because we want the Zaitsev product as our major product. So that's what we get there. Well, our double bond is still not in the right place. We need to move this. So if you compare this with this pi bond with what we have in the product, the final product, you'll notice that that pi bond isn't there anymore. So you have to get rid of it. And how do you get rid of a pi bond? You do an addition reaction. What do you want to add? You want to add something that's a good leaving group because it's not going to stay on the molecule. And a good leaving group are one of the halogens. So we could do hydrohalogenation again. Now watch out. Where do we want the bromine to add? We want the bromine to go as furthest to the right as possible. We're walking the reactive part of the molecule to the right where we have our pi bond. So we want the bromine to add here. Now that carbon is bonded to two other carbons, so it is secondary. The other carbon in the pi bond, this one, is bonded to 1, 2, 3 carbons, so it is tertiary. In other words, we want the bromine to go to the less substituted carbon, and the hydrogen to go to the more substituted carbon. Well, if the hydrogen goes to the more substituted carbon, that is anti-Markovnikov addition. And to get anti-Markovnikov addition with hydrohalogenation, you have to add peroxides, so ROOR. That's the only way that the H and the Br would add anti-Markovnikov, the hydrogen going on the more substituted carbon. Now I'm going to erase that hydrogen so that it doesn't get in our way. It's still there, it's implied in these skeletal structures. Okay, well if we compare this with our final product, we see a bromine here, there is no bromine in our final product, and so we have to eliminate it. So we're going to do an elimination reaction. In other words, we want to add a base. Now, you can eliminate this and get two different products. You can imagine eliminating it, and here let me actually do this in purple. You can imagine eliminating this. So this is the alpha carbon with a leaving group on it. You have beta carbons, that's the carbons attached to the alpha carbon. You can imagine doing an elimination and getting a pi bond going toward either of those beta carbons. If you steal the beta hydrogen on the right, then the pi bond will form on the right. If you steal a beta hydrogen not on the right, but to the left, so over here, then you'll form a pi bond to the left. Which one do we want? We want to use the beta hydrogen on the right, so not on the left. Now let's think about these two products. The one that we want is only monosubstituted. The pi bond that we don't want is tri-substituted. So the more substituted, more stable one is the Zaitsev product, the tri-substituted, and the less substituted, less stable one is the Hofmann product. We want the Hofmann product, the less substituted Hofmann product. So how do you get that? You use a bulky base. This is less substituted. Another way of saying that is it's less crowded. What would prefer a less crowded space? A bulky base. The bulky base you should be familiar with is potassium tert butoxide. So this tert butyl group, that's that little sort of chicken's foot. You have the oxygen with a full negative charge. That's your strong base, strong nucleophile also. And the K, the potassium, is a positive ion that's there to stabilize the negative charge on the oxygen until it attacks. That's potassium tert butoxide. That's our bulky base. That tert butyl group is always there to illustrate bulkiness, the effect of bulkiness. And so that would give us our Hoffman product, which is the final product that we want. So overall, what did we have to do here? What's the full recipe, series of steps that you would want to pour into your cauldron, boiling cauldron, in order to make this transformation happen? First, you'd want to add hydrogen bromide, or hydrogen chloride. And that just by itself, that's going to give you Markovnikov addition, so the bromine goes on the more substituted carbon. Then you want to get rid of that bromine, and you want to form the Zaitsev product. So the pi bond is the most stable, most substituted one that you could form. To form the Zaitsev product, you use a skinny base like sodium ethoxide. Once you have that alkene, you want to get rid of it, right? Because it's not there in the product. So you do an addition reaction. Then you do a hydrohalogenation, because that'll add a leaving group. It'll allow you to get rid of whatever you add. Now you want the bromine to go toward the right side of the molecule where you want the double bond to end up. So you want it to go on the less substituted carbon. You want the hydrogen to go on the more substituted carbon. And so you didn't just add HBr, you have to also add a peroxide to make that add that way. So HBr and peroxides give you that anti-Markovnikov addition of H and Br. Finally, we had to eliminate the Br, and we wanted to do it in such a way that we got the less substituted Hoffman product. And so the fourth step here was to use a bulky base. So altogether, these are the recipes. This is the recipe. These are the steps in the recipe that you would need to use in order to make this transformation happen. Okay, finally B. And B is very, very similar. So you see a pi bond, and instantly you should be thinking, okay, I know what I can do with that is addition, as opposed to substitution or elimination. And confirmation of that is that the pi bond is not there as you go from the reactant to the product. So we have to do addition. The other thing you'll notice is there's a place where we don't have a pi bond and one forms. How do you make pi bonds? Elimination. So you do addition reactions to get rid of pi bonds and elimination reactions to form pi bonds. So we know whatever else we have to do, we know that we at least have to do those two things. Okay, well, we're going to do a similar thing. We're going to be adding leaving groups and then taking them off. And we want the leaving groups and the reactive part of the molecule to slowly walk toward where we form the pi bond. So if we have this pi bond originally, we're going to add HBr. We've seen that. That gives us just one leaving group that we have to worry about. It gets rid of the pi bond and gives us a leaving group that we can use to create a new pi bond in a new place. Now, we want for the bromine to get closer to the pi bond that we want to form. So we want the bromine to go on the more substituted carbon and the hydrogen to go on the less substituted carbon. Right, this carbon on the top is primary, the carbon on the bottom is tertiary. So we want the hydrogen on the less substituted carbon, that's Markovnikov addition. And to get Markovnikov addition, you don't add peroxides, you just add HBr. So I'm going to erase that hydrogen, it's still there, it's just implied. This first step is doing Markovnikov addition of HBr to get the bromine adding on the carbon that's closer to the pi bond that we want to form. Okay, well, if you compare that to your product, we have a bromine here, we don't have a bromine in the product we want, so we have to do an elimination. Okay, we want the pi bond that we form in this elimination to be toward, in the direction of the pi bond that we ultimately form. We want it to go to the right. You could imagine the other place where the pi bond could form is it could go up. It could go in the branch again. That's the other one. Notice that if the pi bond forms to the left, it's really the same as if it forms to the right. Notice that these two things are the same, because if you just flip this over like a pancake, it turns into this molecule on top. So I'm only going to consider that once because it's the same. Those two are the same molecule. So these are the two possible alkenes you could get when you do an elimination with that molecule. The one on the right, this one, is tri-substituted. The one on the bottom is di-substituted. The more substituted, more stable one is the Zaitsev product, and the less substituted, less stable one is the Hofmann product. So we want the pi bond to walk toward where the side of the ring, where we want the final pi bond. And the one that gets closer to in that direction is this Zaitsev product. So we want the Zaitsev product here, not the Hofmann product. To prefer the Zaitsev product, to get the Zaitsev product as your major product, you would want to use a skinny base. Because the Zaitsev product is more substituted, which means it's more crowded. So what can manage a crowded area? A skinny base. And examples of skinny bases would be sodium hydroxide, sodium methoxide, or sodium ethoxide. I'm going to use sodium hydroxide here, just to mix it up. Okay, so now we have this Zaitsev product. Well, if you compare this with your final product, you'll notice that pi bond is not there. So we have to get rid of that pi bond. How do you get rid of pi bonds? You do addition reactions. What do we want to add? We want to add something that just has one good leaving group, and HBr is a great way to do that. So we have hydrohalogenation. But where do we want the bromine to go? We want the bromine to go toward the pi bond that we form. In other words, we want the bromine to go here, as opposed to in the middle, on that more substituted one. So if we look at this, you'll see that the hydrogen is on a tertiary carbon, and the bromine is on a secondary carbon. So what we want to do is have the hydrogen add to the more substituted carbon. That is anti-Markovnikov addition. And to make that anti-Markovnikov addition happen, you would use a peroxide. You would add ROOR. Okay. Now notice, I'm going to erase this hydrogen that's implied there. So notice we're slowly walking the reactive part of the molecule toward the place where we want it to be, which is on the side of this ring. We had it at the top. We added a bromine going toward the side of the ring. We did an elimination reaction toward the side of the ring. And now we're adding another bromine toward that side of the ring, rather than just keeping it in the center there. Well, if you compare this with the final product you want, you'll see this bromine here. It's not in the final product. So what we have to do is get rid of that bromine or eliminate it. Now, to do an elimination, you have to use a base. But what type of a base do we want? One of the products we could get here, the product that we want, is to have the pi bond on the side of the ring. That's what they're asking us to make. But you could do an elimination and get a different product. You could do an elimination and get the pi bond forming to the left, right? The carbon that has the leaving group on is the alpha carbon. Each carbon bonded to that is a beta carbon, and you could form a pi bond to either in the direction of either beta carbon, the one going down or the one going to the left, by removing a beta hydrogen with the base. So we want the one on the left. Now that is a di-substituted alkene. On the bottom, it's a tri-substituted alkene. The more substituted product is more stable. That's the Zaitsev product. The less substituted product is less stable. That's the Hofmann product. In other words, here we want the Hofmann product. Now the Hofmann product is less stable because it's less substituted, but another way of thinking of something being less substituted is it being less crowded. So what would prefer a less crowded molecule? A really bulky molecule. So you can prefer the less crowded Hofmann product by using a really bulky base. And the bulky base that you want to know is potassium tert-butoxide. TBU, okay. And we've drawn the structure for that. It's the tert-butyl group attached to an oxygen, which has a full negative charge that's stabilized by the positive charge of the potassium. So you have the tert-butyl group, that's this here, the oxygen on the end, and the potassium. And that will give you this Hofmann product as your major product in the elimination. So overall, the process that we went through, the sort of answer for this question, would be the recipe you need to add. The first thing you'd have to do is add HBr, could also be HCl. That gives you Markovnikov addition of H and Br. So you have a bromine going in the direction of the pi bond you want to form. Then you need that bromine to come off. You don't see any bromines in the product, so you know you have to eliminate it. Now, there are two ways you could do that. You could get the Hofmann or the Zaitsev product. We wanted the Zaitsev product, so we used a skinny base. And you could use sodium methoxide or sodium ethoxide. Here I'm using sodium hydroxide, another skinny base. After that, we want to get rid of that pi bond. It's not there in the product, and so the way you get rid of a pi bond is through addition. So we added something that we could get rid of later, HBr again. But we wanted this to be anti-Markovnikov. We wanted the hydrogen to go to the more substituted carbon and the bromine to go to the less substituted carbon in the direction of the pi bond we want to form. So to make it anti-Markovnikov, we didn't just add HBr, we added that in the presence of a peroxide, ROOR. Finally, the bromine that we have there needs to be eliminated. It's not in our final product. We could do an elimination either to get the Zaitsev product or the Hofmann product. The one we want was the less substituted Hofmann product, and to favor that, we used a bulky base, potassium tert-butoxide. So those 4 steps are the whole recipe for how you can make this transformation happen, how you can move a pi bond from one place in a molecule to a completely different place by doing successive addition and elimination reactions.